In this unit, we are analyzing multivariable functions. And this notation here represents a multivariable function. And in this first lesson, we're going to really focus on functions that map from R2 to R1. These are functions that graph in three-dimensional space. Let's consider functions of the type z is a function of x and y. For example, consider the function f of xy equals 9 minus x squared minus y squared, and you might recognize that this graphs as a paraboloid. Here, we input values x, y, the ordered pair, and so that's in R2, the Cartesian plane, and that will result or yield a singular response value z, and that is what we say one-dimensional, one value. Let's illustrate this. Suppose I plug in the ordered pair 1, 2 into my function. That's going to result in the value of 4. So I'm going to come over here and say that outputs some value 4 on the z-scale of 4. Plug in another pair. Suppose I plug in the origin. If I plug the origin into this formula, into this function, well, that's going to output a 9. That comes up here, one-dimensional scale. 3, -1, well, that's going to result in the value of -1. So what ordered pairs am I allowed to plug in? Well, I can plug in any combination xy value that I want. So the domain of this thing, its natural domain, is going to be the set of all the ordered pairs xy, such that these ordered pairs belong to all of R2, all of two-dimensional space, the entire Cartesian plane. That's the natural domain of this function. Suppose we decide to restrict our domain to be all the points x, y, such that they are on or inside the circle x squared plus y squared equals 9. I use the inequality to show I want only the points. I only want to input the points inside the circle. So I could still plug in 1, 2. I could still plug in the origin. 3, -1. No, that one's outside of the domain, so that wouldn't be included. 2, 0. So there's a whole variety of different points that I could plug in, provided that I'm inside this domain, because I decided to restrict that domain. Suppose that we say f of xy is actually the height or altitude of some hill at points xy of the Cartesian plane. Well, it might make sense to visualize this. So here's a graph of the function, but because it represents the height of the mountain, this is also a picture of the mountain or the hill, and so as we input values xy, the resultant point comes and lies somewhere on this mountaintop. If we plugged in 0, 0, we know that we get the altitude of 9. Let's take some slices into this mountain. So take the slice plane z equals 8 and the plane z equals 0 and just chop right into the mountain. We see what that does is it creates a trace. And this trace here, I'm going to trace it in red, is a circle. And down here is also a circle. These are called the traces. If we project several of those traces onto the Cartesian plane, then what we get is called a set of level curves. And since f is the height of the mountain, this can be considered like a contour map. Notice here, as I move along this level curve, I traced this one earlier when I showed the plane that cut through the top. Notice here that this number is 8. That means every point along this circle, the mountain has a height of 8. The function's value is 8 along that level curve. Pick another one here. I'm just going to pick a random one. Kind of highlight this. A little hard to trace it exactly, but along this particular level curve, the height of the mountain is always 3. So that's what these numbers are. They're pretty important. They tell you what the function's value is, and as we move along a level curve, the function's value remains constant. So let's change what f of xy represents. Suppose it now represents the temperature of some plate. So this red circular disk here is now going to be a plate, and on that plate there are a bunch of temperatures. Some are warmer than others. We could still represent f of xy as a graph, but this is not a picture of the temperature. It's just a graphical representation of the temperature. You can see as we get closer to the origin, the temperature increases. Now the graph here still represents level curves. It tells us now, we're not talking about altitude, but it tells us that the temperature is 8 for all points along this particular level curve, and the temperature is 3 along this one, and the temperature is 4 along this one. So this is the plate. This is the plate here, and everywhere on this particular level curve, the temperature is 8. If I put my finger right on the origin, then the temperature is going to be 9. And these are still called level curves, but in reference to temperature, we will often call them isothermals. Before moving on to looking at derivatives, let's take a look at this really cool function here. It has some bumps and lumps, and here's another angle of the same function. Now I'm going to take a slice into it, seeing that plane there. I've drawn the trace, projecting that onto the Cartesian plane. That makes a level curve. And then finally here we have a set of level curves. If we revisit the temperature concept, then each of these would represent a temperature, negative 0.2, 0, 0.6. Now here's the thing. If I put my finger on this plate and I move in this direction, you can see that the temperatures are going to increase. If I'm here, the temperature is 0.4, and then I move in this direction, and then the temperature is 0.6, and then this comes out to be 2/3. You don't know that from this drawing. And then eventually, it keeps getting warmer and warmer and warmer until we hit some peak. I find the temperature and having a plate example a little easier to understand direction, because then this Cartesian plane is a physical object that you can move your finger along and the temperature would change. Now, it is worth noting that if I plotted every single level curve, then you wouldn't even see anything, because it would be one gigantic shade of red, because this is a continuous function, so you wouldn't be able to distinguish between two different level curves. Now, if we think of this as a mountain range, we can still talk about movement. So here, I can still move. Let's say I start here. I can still walk in this direction. And what would happen? Well, the temperature would increase, but the altitude would increase. I would actually physically be moving upward to the top of the mountain. So this concept sometimes confuses people. See, we still talk about movement on the Cartesian plane. That doesn't change whether it's temperature, altitude, or anything else. We can still talk about the movement on the Cartesian plane and talk about whether the function increases or decreases. The difference is, in the mountain, you are physically moving up sort of on the graph, and things such as temperature, you're not physically moving up, you're just graphically representing up. And this idea of movement being on the Cartesian plane becomes a very important concept when we start talking about partial derivatives and directional derivatives, etc. Check out this really cool animation made by one of my students, Vikas Varma. There's the same function we've been looking at, and there's the plane. There it goes, slices in. That creates our level curve, and then our set of level curves. Awesome. And so looking at graphs in 3D is really super cool, and we're going to continue to do that, but it's not absolutely essential to see the graph in three-dimensional space in order for us to analyze several parts of this graph, and that's really what I'm going to focus on the second part of this lesson.